concurrent write architecture. And did you figure out what the common program would look like? Okay, explain.
So the priority part will actually, one of the values will be written. So then in the next cycle, when they will, every process will read it back and compare to the value which had to be written. And then the highest priority process values will match. So if the values match, they won't write the original value back. So the priority processor won't write anything, and the lower priority than the highest priority will try to write, and that will get written. So the original value will be restored now.
Basically, every processor would write.
Try to write.
If it's not same, everyone would write. So one of them will,
and that will be the same as the original.
Okay. So again, I'll repeat. First, you read what was there. Okay. Just in case you needed to restore it. Everybody does it. Then the write instruction happens. Okay. And somebody will win. But the remaining, the lower priority ones can read it back and tell that something that got written was not the same thing as that they wrote. Okay, so they all know that it needs to be unrolled, undone. How do they undo it? They all have the old value. They are all going to write the old value. One of them will still win. Okay, whoever among them is the highest priority. Okay, and the old value will get written because now everybody is trying to write the same thing. Okay.
So you also need to prove that the priority cannot be simulated by a column. Give that order.
Actually, no. That sometimes simulations can happen. It will take more steps.
You're saying that the order is necessarily this. Maybe priority can also be simulated.
Priority can also be simulated with common, not in constant time. So here is a simple PRAM program. And we are not doing any initialization over here, how the input got in, how processors got active, and all that. This is CRCW PRAM model. And you are basically checking, right? So that code in the middle says, and this is pseudocode, see the same thing that you would have seen in a RAM model pseudocode, only do's have become do's in parallel. Okay, pardo. Okay, so it says for I equal to 1 to 5, pardo if AI is equal to 1, then output 1. AI is a shared memory array. I is the processor now, right? For every I, there is this very similar to OpenMP style for loop also. Work sharing, right? So every single I is on a different processor and they read exclusively, right? They're reading different areas in A. This is CRCW, but they are allowed to read exclusive. If that value turns out to be 1, then they're going to write into one location output, which has been agreed to by all the processors, the value 1. So in CRCW model, and the goal was, as it says, compute the Boolean OR of all things. And that Boolean OR will appear in which CRCW model? The value should be 1 if anyone is 1. Okay, I'll repeat the question. The program is in the middle, okay, which says all the processors are assigned internally based on their ID, one of the locations of A. They check that location of A. If that location of A happens to be 1, they write 1 into a shared memory called output, shared memory cell called output. Okay, they are all writing into the same cell called output.
It's fine. So any one of them write one, that could be. And if it's common, that is priority or any.
If it's common, it works.
Because everybody rewriting one.
Some will not write one.
So let's look at each one of them. The simplest is random. Right? Means somebody's result is going to get written. Nobody is trying to write a 0. Right? So if your value is 1, you write it, otherwise you keep quiet. So if the people who have 1 are trying to write and somebody's result got written, and somebody's result must get written. Random says, I don't know whose result is going to get written, but somebody's result is going to get written. 1 will appear. Okay? In case of priority, again, one specific fellow's 1 will get written, whoever priority is the highest. It will still be 1. Okay? And the third, everybody who is writing 1. Okay? So whatever the model may be, is going to compute the Boolean OR. Okay? That's not always as nice as that, but in this case it is. Okay, we are going to add a few things together. Okay, I've got n objects, values, in n locations in the shared memory, n cells in the shared memory, and I'm going to assume order n processors. Okay, n processors. How can I add in CRCW PRAM? Exclusive read, exclusive write.
So each processor can access the index which is equal to its own process ID.
Okay. So everybody has, and there are n things. So everybody has read one of those n things. Then what happens?
No two processors will read the same.
Two processors will read the
No
same.
two processor will read the same.
Will read the same value. That's correct. But then proceed. You want to start with n by 2 processors, okay?
Each processor reads 2 values.
2 values.
Add those 2 values and write it.
Which 2 values?
The values which the processor reads.
That's a cyclical answer.
See, every processor knows its ID, so you
Yes.
pick that. We can divide the whole array in the position. By 2 blocks. By 2
So you can read I and I plus n by 2. Okay? Or I and 2i. 2i plus 1, sorry. 2i and 2i plus 1. That may remind you of something. Heap, exactly. We are building a tree on this array. Okay. So you read n things, and everybody is going to have read 2 things. They're going to sum it together. And where will they write?
in one of those 2 blocks.
They can override.
They can assuming that the input is not needed anymore, you can overwrite in one of them. I by 2. You want to write in I by 2? I. If it is needed, means you cannot overwrite, then you will write in some temporary location. Right? But this time, keep doing this on temporary location. Or for that matter, you might say, I'm going to just copy over the original array into a temporary location and do this summation in the temporary location. Okay, so that was one step. In one step, everybody read 2 things, summed it, wrote 1 thing. How many such steps will be needed? Log n, right? Again, the place to read from and write will come from that heap structure. Right? At each level, you know what your children values are, indexes are in the array. At the end of it, you're going to have one processor that's going to read 2 things and write 1 thing. Okay? At each level, some processors will be turning themselves off. Okay? How? You simply check the level right? And each time you could keep reducing the number, right? Okay. And you can do it in many different ways. So there are log n steps involved.
But you said that all the processors will do the same task, right? That excludes those processors which are off.
Yes, right.
That
So
should have been mentioned in the right. I mean, if all the processors are doing the same, then those processors.
So that's a technicality, right? You can say that the processors were not reading one of those, are reading from a location called infinity. Okay, and they're writing into a location called infinity. So that detail is not necessary to manage as a part of the program itself. In fact, even if the processor does something, doesn't mean it has to write something. It might read, do some computation, read more. It doesn't have to write something. So that I think probably is a good thing to mention, that all these steps are optional, right? Which means they can all be reading or doing nothing. What you cannot do is while someone is reading, somebody is writing, and somebody else is doing some local computation. All right. So the time will be log n. The number of processors you have used is n by 2. Okay. First step was n by 2, but then it kept going down. But the maximum number of processors at any step was n by 2. So you have used n by 2. Okay. The speed up, what's the sequential time to add n things? N steps, right? And minus 1 additions. If you compare it to that, then you've got n over log n speed up. Okay, so these are, if you remember from earlier slide, the same statistics. The efficiency is speed up over the number of processors. Okay, and we have used n. Again, this is order. We're not worrying about n and n by 2. The work done is the number of processors times the number of steps. Okay, so the work done is n log n. And that's where we are going to now figure out what happens if I have p processors, not n. Okay.
We did not do any operations.
We did n operations, but we couldn't have done all the n operations at the same time using n processors.
So why do you say work is n?
The work is the total number of steps multiplied by the total number of processors.
But this
Even some of them might be
We turned off.
Yes.
you can do then equal.
So this is not the summation of work done over time. This work done says how much parallel work has been done. Okay.
But when the processor was switched off, no work was being done.
But they couldn't have done any other work. If there was some other work for them to do, then they should have been doing it.
Because there is no other program running.
Right. We're not talking about contexts and all that. Talking about that machine running this program, and at some stage, because your algorithm is going to blow up computation, you can do it in lots of processors. Then keep it idle for a long time. We charge it to your algorithm. Okay. So if you can manage to keep the processors down at every step, keep all of them busy, you're probably going to get a lower work done. Okay. And the work done is going to be the most predictive statistic. When you run it on an actual machine with only P processors. Okay, we'll talk about that in more detail. But let's look at a couple of other algorithms. This is the membership problem. I've got n things written into n places. Right? Membership problem search is a search problem. Okay, and I've got a query x. I want to know if this x exists in that input array. Okay, and we can write it at a high level. So in the first step, everybody gets the value x. Okay, In the second step, everybody checks if the X exists in some part of the input. And in the last step, they're together going to decide if somebody found it. Okay. Let's look at each of these three steps in the different models. We are looking at, in this case, EREW, CREW, and CRCW common. Okay.
Isn't this similar to the output equal to one program? Similar.
Not all of it. Yeah. Yes. Not all of it, but yes, the last step is. So the first step is broadcast so that everybody knows what we are looking for.
No, but why is there a separate file?
Because in EREW, that X cannot be read by everybody in the same. Yes. For concurrent read, everybody will read X in the first step. Okay, so in CREW and CRCW, that cost is written as 1, order 1.
So what is P? Number of processors.
P is the number of processors. P is the number of processors, yes. With number of processors in this case being a given value rather than n.
Sticks is again from the model, right? The model says we can have that.
Yeah.
Exactly. So we are going to now move towards how do you take this model or a program in this model and talk about a real implementation of this model. Okay. All right.
Why is the cost of broadcast log P in EREW?
The model doesn't specify this.
Sorry?
The model doesn't specify this, right?
No, we are going to have to come up with the algorithm to do it. Model has no notion of broadcast.
So the interconnection that may be there between the processors, you can assume the most favorable one. In this case, for example,
No. We are not going to assume anything about the interconnect.
so
All the information is shared by writing to some place and somebody else reading from it, which each takes constant amount of time.
So the interconnect is not among the processors, but interconnect is connecting a processor to the shared memory. That's it.
Interconnect is exactly connecting it to a shared memory, but it's hidden, right? We never directly say talk to the interconnect.
No, I mean talk to the processor.
No, we never say talk to the processor either. Right? There is no send receive type instruction. That's what we will do in a distributed memory model. In the shared memory model, it's a strict, pure shared memory model. You write to a common place and you read from a common place. Okay? So how do you get X to every processor knowing that they can't all read the location of X in the first clock? So there was a question, why is it log of P?
So when one reads the value of X, he then writes it for another processor to read it. So it divides by 2 at each step.
Multiplies by 2. Right? So the first processor can read X and read into, we're not caring about how much space we use, right? So we have plenty of space, shared memory space. We just allocate some temporary area, and the first processor reads X and writes in one more location. So now we have 2 places where X is. Right? Now 2 more processors will read those 2 things, and each will write 1 more. So now we have X in 4 locations. Okay. Next step, we'll have X in 8 locations. So how many steps to get it into P locations? Log of P, right? The local computation, we have determined that every processor will take n over P section of the input and search for X in that. Right? So in n over P steps, they'll read in any model, exclusive, concurrent, all models. They'll read from their exclusive part of the input, check if that value is equal to X. If it is not, leave a flag off, otherwise turn on a local flag, and then keep doing this for all the locations. Okay. So at the end of it, somebody may have found it. It's possible that more than one finds it. And they have a local variable called f, This is local memory, as much as you like. And now everybody needs to agree. They need to come to a conclusion about whether somebody got an F.
Sir, why are you taking the common mechanism? Should it not be arbitrary? Because in common, if all
I'm not taking any mechanism. I'm just giving you 3 examples.
concurrent read common model, if all of them have found that X is present, then only it is to be written. Otherwise, it is not written. Okay?
It is
Answer
not,
won't be.
not right. It is not found is wrong, right? It is not right.
You initialize with 0, right? And if somebody has found it, they're going to write a 1.
That's arbitrary.
All of it, right? We just saw that OR works for every single variant of the concurrent write. Okay, and so here we don't need to worry about which type of concurrent write it is. So although I have said common, it would be order 1 in all of them. But how about when you have exclusive, right, which is both first and the second column?
Something reverse of this log p.
Reverse of the log b, right? Instead of broadcasting, you're collecting. It's very similar to add, right? You're not adding, you're saying compute OR of these things. Okay. Similarly, you can think of the activation. We said there is a start protocol. The start protocol can be done the same way. We have the starting process, which we just say is one with ID 0. In steps, just like we did log reduction or log expansion, in log p steps can tell everybody to become active.
How does it tell to be active?
It tells to be active. Every processor is reading, right? So they don't know where to read, they don't know where the input is, they don't know whether a program is running or not. So they're just reading from some arbitrary location. And processor 0 is going to now know that we are actually running a program with that data, that input, that, etc. So now it's going to tell that whatever it has learned to everybody else. It's like broadcasting. You all start working on this problem. Okay. All right. So we've looked.
But they are reading, writing from arbitrary location. How will they know that now it's time to read from this particular?
That arbitrary location is where you write.
That arbitrary location is known.
Has to be, yeah. So there is some hardwired things in the model that everybody is reading location number 0 if it is an exclusive. If it's concurrent read aloud, in which case you write 0 to, or you write something, whatever you want everybody to know, to location 0, and everybody reads it the next clock. If only exclusive write is allowed, everybody is reading from their own respective locations, cells, and you've got to write that new value in all of them. Okay.
But in exclusive write, they have to read on alternate cycles, right?
They have to read. So those 3 together go together. So if you're calling alternate cycles, then
I mean, so it can just happen that they are reading, reading.
I'm not sure. When they are reading from some location which will be filled with some input at some point, which says now the program is over there, or now the data is over there, or whatever. Okay, and so that site is going to get filled in log n steps, log p steps, if you have p processors. And if you're exclusive read model, then it takes log p to initialize your program. That's all. Okay. Any questions on the basics of the model? All right. Okay, we are running out of time on this session. Work is what exactly? Number of processors multiplied by the number of steps you took. Okay, And so now suppose I've got an algorithm, and in each time step, let's go into the next level detail. At each time step, we are doing some amount of work. That work is how many processors were active. Okay, so in our summation, for example, the first step, n by 2 amount of work was done. Second step, only n by 4 amount of work was done. Then the third step, n by 8 amount of work was done, right? If you're going to count that amount of work done with n processors, and now if I have p processors, I know that any amount of work that was done in one step was done in parallel by n processors, meaning that p processors can also do that in parallel. What they cannot do is do some of that and some of this, because they may depend on each other. Okay, so the p processors can only take those n things or some function of n things that was done in one step and allocate it among themselves and do it among, so wi things was done at step I. P processors will each take wi over p of it and do it. Okay, when I actually only p processors, not whatever the input is assuming or the algorithm is assuming. Okay, now let's add it together over all the steps. That's the amount of work that a p processor PRAM will actually do, or that also says that's the number of steps that it's going to take, because what was done in one step by wi processors is now taking wi over p steps, because there are only p processors to share that load. Okay, so you add it together, and the summation of wi over p, and each step this takes a ceiling, right? Because if there is one process, if there are 10 things to do and only 3 things to do them, then there'll be somebody will be taking 4 steps. Okay, so that thing got done in 4 steps, and the sum of that is equal to w over p, w being the summation of all the work, plus the time. Time is the number of steps that the original PRAM algorithm took with however many processors it assumed. Why? At each step, you're saying, I'm doing wi over p ceiling. So when I take wi over p and add it together inside, what do I get? P is the same in the denominator. All the wi's get added with the total work. Right? Total work divided by p. But how much extra might I have added in wi over p ceiling?
Number of steps that are
At each step, I could have at most added 1, right? 1 minus some epsilon by taking it to the ceiling. And we did this tn times because the original algorithm took tn steps. So we have added tn more things.
So what is wn? Is that the same total version as we defined earlier?
So tell me, what is wn now?
It is the sum of wil.
It is the sum of wi.
It is not the work done as we defined earlier, number of process into the number of steps.
Exactly. It's related. We'll talk about that also, or maybe you'll have a question about that. Okay. What we are going to do next week is how to simulate a general processor PRAM with a PRAM which is this was just an analysis of how much time it would take. We talk about an algorithm that will blindly take an n processor program or any size processor program and run it on a p processor PRAM. Similarly, we'll take any processor, any program that runs on m cells and run it on m prime cells. Okay, so if I have only limited amount of shared memory and only a limited amount of processors, I can still simulate whatever the PRAM algorithm did at the cost of some number of steps, of course, but it can be done. Okay.
Can you explain the last one point?
So how did that floor ceiling turn to floor?
Good question. Find out. All right. So we were discussing the last time this notion of work time scheduling. We will come back to it. I hadn't finished talking about it, but we'll relate it to some of the other things we'll talk about shortly. So I'm going to bring it back when it makes sense. The first couple of things we want to take a look at it is at a theoretical level now, where we're looking at whether PRAM makes sense. Okay, we said there's infinite amount of memory, there's infinite amount number of, not infinite, but as many as you need, some arbitrary number of processors, unlimited number of processors, and unlimited memory. Is that a handicap? Meaning, with that assumption, am I breaking the effectiveness, the applicability of this model? Okay, so one of the theorems that we are going to prove, or lemma if you will, is that suppose I give you a PRAM algorithm that uses some f of n processors. Okay, in general, p processors, so according to this lemma. But I want to run it on another PRAM that only has p prime processors. Okay, p prime less than p. Could I do it? Same amount of shared memory, same amount of local memory. Okay. In fact, we don't say anything about local memory. Local memory, we are in fact going to use as much local memory as we need in order to do this simulation. So we don't restrict the local memory, and that makes sense because we can make local memory quite big. So the RAM model assumes infinite local memory and is quite useful. So if I have only p prime processors, I give you a p processor PRAM algorithm. How would the p prime processor PRAM run this algorithm? Kind of like context switch, right? So each processor, in fact, this lemma should already be telling you. So any problem that can be solved on a p processor PRAM in p steps can be solved on a p prime processor PRAM in order t prime times p divided by p prime steps. Okay. Essentially, what you're going to do is have each. We are assuming here that p prime is smaller than p. If it's bigger than p, then there's not much to be done, right? You just have the extra processors be inactive. But if you have fewer processors than you need, then you say I've got p processors that I need, p prime that I have. I'm going to have each processor act for, be a proxy for p prime over p of the original processors. Okay. So we are going to call the original processors the ones we are simulating, the simulated processors, p of them, and p prime the real processors, available processors. Okay. So each processor will simulate or will work for p over p prime virtual processors. Okay. What does it have to do? So how was the algorithm going to work? For every step, it was the algorithm said, you read from here, you do this local computation, you write over here. Okay. So now we are going to do that in a loop. But nobody is saying is staying inactive. Right? There are p prime processors working. Each processor is simulating multiple p prime over p of the virtual processors, the imagined, the assumed number of processors. And so I am one of these processors, and I have to simulate p prime over p of them. Okay. So the p prime of p of them, each one had a read, local computation, write step. So I have an array of reads, an array of local computation, and an array of write to do. what do I have to do? I have to do all the reads, read them in some local array I have. Then I perform the local operation in this local memory, each one after the other, and then I do all the writes. Okay. So I do all the reads that they would have done one after the other. So they would have done in parallel, I'm doing it in sequence. Doesn't make a difference. They're all reads. They would have done their local computation in parallel, I'm going to do this in sequence. Doesn't make a difference. They're all independent. I am taking one area of my local memory and thinking of this as the local memory of processor 0, another area processor 1, and so on. So they're all independent of each other. And similarly, they were all going to write in parallel. I'm going to write in sequence. But after these many steps, I have simulated all of them. How many steps? Approximately one step, right? So if you say 3 steps are one step together, then I have done not one step like this, but 3 times the number of processors sub-steps, which means as many steps as the number of processors I'm simulating.
What would you write? So you have like 4 or 5 times of write.
Yeah.
How do I simulate common write?
Yeah. Concurrent.
How do you simulate common write? All can be done. So if we have a common CRCW PRAM, then we'll simulate a common CRCW PRAM. How would you do that? All these writes, if they're writing to the same address, should write only if they're writing the same thing. So what would you have to do?
Locally check that first.
You can locally check that first.
Because it is in the memory of the same process.
It is locally in the local memory of the same process. Right? How much time does it take to check that? As many processes as you're simulating, right? You can do brute force. You don't have to do anything smart. So that doesn't change the number of steps needed to perform the write. Okay. If it is random, then you don't have to do anything. You just keep writing. If it is priority, then you write.
The processors that you have been allotted with, you can sort them into the last, the highest priority at the end.
Can you do highest priority at the end?
So that write overrides everybody.
But there are P prime of them independently doing, and I have 3 writes to that memory location, and some other processor has only 1 write to that memory location, but is the higher priority one. So when does that write? If that guy writes immediately, then after 3 steps, this guy will have overwritten it. So you have to do somewhat the opposite of what you were saying.
Each processor first do this high priority.
No, but then different people will be writing to different memory blocks.
Which is perfectly fine.
No, but I have a processor which writes to some memory block, and some other processor is also which also writes to that. It is of a lower priority. So how do I synchronize the 2 processors?
So this processor has written its stuff first, and this processor is going to write its. So this has done 1, this has done 2 to the same location. Okay. So this is the higher priority, and this guy's first was the high. You sort it in the order of highest priority. This highest priority thing gets written first, and this highest priority thing gets written first. The higher of those 2 will get written. This guy now second write won't do because it has already done a higher priority thing.
Right. So what I wanted to say was the second write was to address which was different from the common address.
Exactly. Then it's perfectly fine. You write to an address only if you haven't written to it before.
That's okay. So I mean, you have some data to be written to a shared memory, and some which is not being written to.
Which is not common. Which is not a common address, not a conflicting address.
3 processors ABC. A and B want to write to 1. B and C want to write to 2. How to do that?
A and B want to write to 1, and B and C want to write to 2, right? They're going to figure out, first of all, A and B will decide that we are going to take the highest priority thing that we are writing, right? And we are going to write that first. If there is anybody's common, then the automatically hardware will take care of it, right? Because P prime processes, hardware will take care of it. If not so, then I'm simply going to write.
How do B and C synchronize?
B and C synchronize.
Because in B, the processor is the second one. A and B both have one processor each. B has two each.
We are assuming that everybody knows how many processors everybody has, and in fact, in this case, for simplicity of proof, you can start with the assumption that everybody has the same number. That doesn't do anything to his example.
Yeah, so I modify the example. So I say 1 and 4, and I make it even. That's all.
Yeah.
So then, how do B and C synchronize? So I can understand that one writing to a particular memory location together can be synchronized in fashion that the first write will happen in that memory location. If there are multiple write memory locations, then what happens?
You basically, the basic rule is that if you are writing to a higher priority, so it's not a high priority memory location, which is what I was going to say. It's a high priority processor, right? So this processor has n things to write. This processor has n things to write, okay? And you have to figure out which order you're going to write them in, okay? And you don't know where this guy is going to write. There are n memory locations that you're going to write. N being the number of, because you're simulating P prime by P processors, or rather P by P prime processors. That many memory locations is what you're going to write. All right, this is one way to do it. You basically write your values in whatever order of these memory locations you care for. Okay, the issue was you don't know what order to write the memory locations in, right? So you just write them in any order. But you're going to have to read it back to find out whether it got written or not, whether anybody else wants to write that memory location or not. Okay? You're going to do it P prime by P times. If somebody else wants to write the memory location, you need to know what its priority is. Okay? If it is higher priority, then you don't want to write it again. So now in every memory location, you write what you wanted to write as well as the ID of the processor that was going to write it. So each memory location becomes a tuple.
You can write the priority there. Instead of that.
You write your processor ID, who's going to write, who wants to write there. Whoever won out, his value is going to get written here, right? And if you didn't win out, then you are going to know it, and you're not going to write it again. Okay, so in P steps, you'll have figured out who actually should be writing it there.
So actually, what we do usually in those cases, we maintain one Boolean array along with those memory locations and maintain 1 0 1 0 if it is higher or lower, and so that
Who's higher or lower?
in some sense we maintain some sort of mutex, right, for writing. If it is higher, then we do not let it write. Otherwise,
No.
that is similar to the maintaining tuples of.
I understand, but it's not only that there is a tuple, because you're not simulating a priority write on a non-priority write, which is what you would do by what you were saying, right? The underlying hardware is still priority hardware, but only it recognizes priority among only P processors. P prime processors. Whereas you need to figure out the priority among the P processors, the original P.
So originally, whichever was the highest priority processor, that has been inherited to some IFP.
Yeah, one of the available processors.
So now that becomes the highest priority processor. And so if we have sort of tuples, then we know that processor, whatever writes, that is going to be used. otherwise it's not written.
No, but the other processor is going to write it at one of the other steps. That's the problem. Right? If they were writing at the same time, then there was no problem. But when it's going to write it at one of the other steps, it must not overwrite something that someone else has written in that same step at a higher priority. Right? So it must, before writing, it must read it and write it again. Only if among the simulated steps, nobody has written to it, nobody with a higher priority has written to it before. Okay? So still P prime over P simulation steps are needed, rather P over P prime. But you write to it by reading it first. So each write operation has turned into a read, do some local compute and write operation, another read write. Okay?
So you're saying like the entire steps are being broken, like this set of tasks which is one of the problem needed, set of processes needed was given free and it has set of rights, the end of the set of steps. And but now the priority will be like on P dash.
Priority is on the original P.
On the original P, now all of the processes which have come into one P will have same priority. They are two, if there is distinguish between the rights.
Yeah, internally you can distinguish, right? You are simulating 5 processors or 4 processors, then you know that you're simulating processor 8, 9, 10, 11 and 8 has a higher priority than 9, 10 and 11. So that is a local computation. But the issue is that I am writing k things, right? P over P prime things, and some other processor is also writing P over P prime things, up to P over P prime things, right? And in some arbitrary order. So what I write here may have a conflict with that fellow writes over there, right? If I have a higher priority, that fellow must not overwrite. You can only, because it's a PRAM hardware with P prime processors, you can only write P prime things concurrently, right? So you can't say I'm going to write these many things. Whereas that's another way of simulating, because technically in PRAM, there is no limit on the size of the memory. Each memory cell, nobody says it's a 4-byte memory cell. Right? So memory cell can be as big as you like, enough to hold all the processor's IDs. So now you can simulate by you writing your part of the data into your slot. Right? So each memory cell has become an array, and all of them together somehow tell you what the value is. In which case, everybody gets to write in its slot, but the when you read, only the highest priority thing is going to get. You're going to only use that. Others you are going to discard. You can read the entire thing in one shot because that's one memory cell. Okay, but that's a technical way of doing this. More algorithmic way of doing this is you simply add the information of who is writing. Okay. All right. Everything is clear on small number of processors?
So at the end, who reads the data?
Before you write, you have to read it. So,
Every time.
yes, every time. So k writes are not just k writes, have turned into k steps of read, local, compute, write. Okay.
So it's like we have, for example, 3 processors put into one processor. Instead of, why can't it collect the 3 writes and then make a sort of logic and then write one of them? That's how it works. 3 writes, and then if they have common, then you write one of them depending on the priority.
But it's not just common among them that you're interested in, right? One of your writes may be common with one of the writes of somebody else. And because you have said, I'm going to write them in this order, and there's just some 3 random memory areas, right? Memory cells. You're writing them in this order. There's some other 3 random memory cells. You're writing them in some arbitrary order. You can even say, I'm going to write the smallest, then the biggest, then the bigger, and then the biggest. Doesn't make a difference, because these are 3 random independent values. but one of them might match. And you don't know whether that guy's third and your first matches or some other. All right. What if I had not enough memory? And you now, the same idea will apply. Instead of M memory cells, I've got M prime. So shared memory is limited. But local memory is not. If you want more local memory, I can give it to you. So basically you are simulating many processors inside one, right? Now you will be simulating many memory location cells inside one. Right? So how do you do that? You basically make a local representation or a copy or a replica of the shared memory. What you wanted, right? You wanted M cells over there. You only have M prime. So I'll take the local memories and distribute these M locations into their local memories. So everybody now has M over P local memory cells dedicated as the shared memory. So now the shared memory has been distributed. But you still have M prime cells over here.
M over P.
Right, there are M shared memory cells that you wanted to simulate. You wanted your algorithm to be able to have, but you only got M prime. Real hardware only has M prime shared memory. So I want to write M different things, possibly, potentially, over the period that the program runs, right? So I'm going to take those M different things that it was going to access as a shared memory and allocate it among the P processors. I said, you keep a replica of these M over P cells, you keep a replica of the next M over P cells, and the last M over P cells is handed to the last processor. Okay? But now, how do you share? So you still have a shared memory, right? So as long as one memory cell is available for every processor, one shared memory cell, you simply figure out which of the shared memory things you wanted to write. You write that thing at that memory cell and keep the others local to you. Right? So how do you make sure that you have written, and when you write one of your values, one of your allocated values, others can see it. And over the period of the step, the original step, you have to make sure that everybody gets a chance, because you don't know who wants to read what. So you're going to take all the cells that you are responsible for and put it in the shared memory one at a time. Okay?
Constantly.
One step each. Right? So you're basically in a loop. You have to say, now you take my memory location number 0, now you take my memory location 1, now you take my memory location 2. So you have written one at a time. But it's not a tight loop, right? You're not just writing, because somebody else has to read at some other time. You're going to turn it into an entire step. Everybody writes their 0th location into the shared memory, and then everybody gets a chance to read. If you wanted to read it, read it. Didn't want to read it, keep quiet.
So basically, whichever processor wants to write it, writes in the main memory, shared memory, and the processor which has that shared memory part in the local memory picks it up and stores it.
Right. Again, you are allocating the shared memory among the different processors. And because you are responsible for exposing your part of the shared memory to everybody else, you are going to do that by exposing every single cell you have.
For each step, there is so many writes which have to be like extra steps.
Yes. There are so many writes for one original PRAM step. Right? Now you have taken each of them and turned into a full step. So you said, now I'm going to write my location 0 into shared memory location 0. Processor 1 is going to write its location 0. It's 0th, everybody has an array of memory cells now, right? It's going to write its 0th cell into the shared memory address 1. Processor 2 will write its 0th cell into shared memory address 2. And in one step, everybody has written one value. Okay, P processors have written P things. But we are saying that we have at least M prime processors. That's why the number of processors available is max of P and M prime. So as long as there are at least M prime processors, all the M prime cells have been written by somebody. And now the next read step, anybody who wanted to read that value is going to read it. And now all the processors will write the second element of their array into the shared memory.
So sir, P minus, suppose P is greater than M prime, then P minus M prime processors remain idle.
Yes. For writing part. This is just the writing has turned into a big loop. After that, everybody is going to read their thing and do the local computation that's going to happen anyway. So you're simulating, taking the M cells you have, partitioning it into M prime segments, blocks, whatever you want to call them, assign each block to a processor, and have the processor essentially use the shared memory, its section of the shared memory, as a staging area. And after as many iterations as M over M prime, because that's how many memory cells each one is responsible for, you have exposed all of your memory cells. So anybody who wanted to read anything in the original PRAM has got a chance to read the proper value in one of these rounds that we did. All right. In terms of evaluating performance, we've looked at a notion of how many processors we are going to use, right? Because now the algorithm is just saying, if you give me P processors, I'm going to do this in time T. Okay, so P becomes potentially a function of N, the number of things in your input that you're processing. And the time taken becomes a function of the P you have and the N, which is the input size. Okay. So instead of having just one metric that we used to have, how much is the time taken? Is it an N log N algorithm or N squared algorithm? We have now said it is N log N if you have N squared processors. So now how do you compare two algorithms? And that's where we use the notion of work. And we'll just go through a few things now to see why work is what we should be considering. But what it is saying that is that if I have you give me two algorithms, one takes P1 processors and takes T1 time, the other takes P2 processors, it takes T2 time. I'll say, hold on, tell me how much work is each doing. One takes W1, the other does work W2. Then I'm going to take the one that does smaller amount of work. So for example, if I've got something that takes time N, order N, but does also work that is order N, I'm going to prefer this over another one that is faster, takes log N time, but the work is N log N, okay? Generally speaking. We'll dig a little deeper into that very shortly. And if two algorithms have the same work, then we'll look at the time. You do the same amount of work, but who does it in fewer steps? Okay, that fewer steps means what? That work is more evenly balanced among steps. Right? We'll also be looking at how scalable it is. Right? No, we're not just saying it is, if I have a value N, then it goes up by this much, but we'll say how well does it scale when your N goes up. Okay, so there are two notions. One is of absolute speed up, which says if I had the best sequential algorithm, it took time t0. Your parallel algorithm takes time t1. So the speed up is t0 over t1. The other is more relative, and that's why the term relative speed up. It says that if I have one processor, you run your algorithm, not the sequential algorithm, your PRAM algorithm. If it had only one processor available, how much time would it have taken? If that is P0, and on n size input, it is Pn, then the speed up is relative speed up is P0 over Pn. Okay, so usually relative speed up is going to be important. Not that absolute speed up is not important, but if you've got a good relative speed up, it's saying that you've got an algorithm that scales well. As hardware size will change, it is going to do well. Okay. Question.
And the number of processors, assume that the number of processors has gone down to 1, then P, then do we also decrease the input size because the order will actually reflect n by P.
No, we don't reduce the input size. We just say that it's the same algorithm. It's just the number, because algorithm now has two parameters: how many processors it takes, and what's the input size. So I keep the input size, take the processor down all the way to 1, and then compare that speed to if I take the processor to some other higher value. Okay, let's stop here.